All right, in our third video for chapter 5, we're going to look at thermodynamics in 5.6 through 5.9, and then see how that relates to the stability of alkenes. Because as it turns out, not all alkenes are created equal. Okay? So hopefully you remember from Gen Chem the difference between thermodynamics and kinetics. Okay? Thermodynamics, we're looking at relative amounts of reactants and products, right? How far a reaction is going, the extent to which a reaction is occurring. Okay? But kinetics is the rate of a chemical reaction, how fast something is converted. Okay? Either reactant to product or product back to reactant. So those are different concepts. It's easy to confuse them. Make sure you know both, right? Thermodynamics is looking at how much of something is formed. Kinetics is looking at how fast something is formed. Okay, so even though a reaction might be favorable thermodynamically, it might be so slow that it never occurs in a reasonable time frame. We also have an equilibrium constant. Hopefully this looks familiar from general chemistry as well, right? Equilibrium constant gives us some information about those concentrations, which of course depends on their stability. And the equilibrium constant, KEQ, will tell you which side is favored. Okay, relates to like the Ka that we saw in chapter 2. Whatever is more stable is higher in concentration at equilibrium. So if we had a large KEQ in this case, C and D would predominate. That means the products would outweigh the reactants. Okay. And some terms that maybe are new, maybe are not, depending on your Gen Chem background. Okay. Exergonic and Endergonic. Okay. This scheme on the left, A, right here, is an exergonic reaction because there's been a net negative in Gibbs free energy. There's a negative delta G, that means exergonic, versus endergonic over here, positive delta G, right? Going from reactants to products. I look at delta G, energy of the products minus energy of the reactants. If it's negative, exergonic. If it's positive, endergonic. And remember that we can relate that to the equilibrium constant as well, using the formula on the bottom. Delta G naught is equal to negative RT natural log of the equilibrium constant, okay? Where R is the gas constant, T is the Kelvin temperature, right? And remember that delta G naught indicates concentrations of 1 molar, temperature of 25 degrees Celsius, or 298 Kelvin, or pressure of 1 atmosphere. So if I'm doing a reaction in the lab, for example, I want something to occur, that means my products will be favored at equilibrium. So for that reaction to be successful, I would want either a positive KEQ or a negative delta G, 2 criteria that relate for spontaneity. Okay. So all of that summarized right here, slide 48, delta G of the products minus delta G of the reactants. It relates to those 2 terms. Make sure not to confuse them with exothermic or endothermic. Those 2 terms on the bottom here correspond with enthalpy, delta H. These are for delta G. Okay. And where do we relate Gibbs free energy to enthalpy? Right? You should remember this equation from general chemistry as well. Delta G equals delta H minus T delta S, where we have Gibbs free energy, enthalpy, right? Heat of the reaction, and entropy, freedom of motion, yep, as well as the Kelvin temperature again. If you don't recall those definitions, right? Enthalpy, we're thinking about the energy in bonds, right? The heat given off or consumed during the course of a reaction. If we're forming new bonds, heat tends to be given off. If we're breaking bonds, right, then heat tends to be consumed. That's where we're using exo and endothermic. Entropy is more of a measure of the freedom of motion, the randomness, and restricting the freedom of motion decreases entropy. If we're forming large complex structures, for example, that has a decrease in entropy. But if I'm splitting a molecule up, that would have an increase in entropy. Keeping in mind that entropy is temperature dependent, and that can have an effect on the reaction as well. For a favorable reaction, right, delta G equals delta H minus T delta S. If I want a negative delta G overall, That means I want a negative value for enthalpy, being exothermic, and a positive value for entropy. So if I were to write that in the form of words, I would say the formation of products with stronger bonds and a greater freedom of motion causes a reaction to be favorable. Stronger bonds to get the negative value for enthalpy, greater freedom of motion for the positive entropy. Okay. So how do I get a reaction to be more favorable? This should sound familiar from chapter 13. You had me for Chem 1560 when we learned about equilibrium, right? Le Chatelier's principle. If I want to increase the amount of a product, okay, I can change the equilibrium to drive that forward, either by removing some of the product, right, distilling it off and causing the reaction to make more, because if I have a decrease in concentration over here, my reaction will shift right to make more product, or I can add more reactant. Adding more of A or B, increasing these concentrations, would cause my reaction to shift right. There are also coupled reactions. These are really common both in organic and in biochemistry in the human body. If I have an endergonic reaction that's immediately followed by an exergonic reaction, that's a coupled reaction. It's kind of a double application of Le Chatelier's principle. In this first step, the endergonic reaction, very little bit of that B is made. But if this is a largely exergonic reaction, it lies far to the right. If that reaction to make C is pulling B out immediately and driving that concentration down, it's going to force this reaction to shift right to make up for it and eventually drive A to B to C. And that's how your metabolism gets over those necessary energy barriers. So how do I calculate delta H and how does this relate to organic? This is where we're actually getting into the new stuff. Everything up to this is probably review. Right? Maybe you had to refresh your memory to general chemistry, but you've seen most of it before. Now, calculating delta H, right? These enthalpy values are calculated as shown on this slide from bond dissociation enthalpies, similar to what we did in thermodynamics in Gen Chem. Right? Looking at this reaction here, I calculate these bond dissociation enthalpies. I have the product, I have the reactants. So I look at this reaction, negative 22 kilocalories per mole, something that's easy to calculate. And so it's used to quickly approximate if a reaction is favorable. That only really works if it's a low temperature and an insignificant entropy change, so that we can just kind of compare delta G to delta H. If it's negative delta H here, low temperature, insignificant entropy change, then it's probably a negative delta G. Okay. So this would be a quick, it's not a hard and fast rule, it's just a quick approximation. Yeah, it looks good at first glance anyway. But things like the solvent, for example, can also drastically change that value. Okay. And here's an example of a bunch of bond dissociation enthalpies. You add those up to find the value, as we did here on slide 53, for a molecule as a whole. Not something that you would necessarily be asked to do on a test, but it's something that's done using those bond dissociation enthalpies to determine the relative stability of alkenes, as I alluded to at the beginning of this video. And this is specifically done with reactions that are known as catalytic hydrogenation, right? And it's right there in the word hydrogenation. It's adding hydrogen to an alkene. Right? You add hydrogen, each, right, H2, hydrogen, elemental hydrogen. Each of the hydrogens go on opposite sides of the double bond, so each of these carbons get an H. So the net result is you go from an alkene to an alkane. Now, if you just add an alkene and hydrogen and nothing else, no reaction would happen. Okay? This catalytic hydrogenation needs a catalyst. Right? So it's a metal catalyst. Palladium on carbon or platinum can be used for a catalytic hydrogenation. You need that catalyst to weaken the HH bond here in hydrogen. Yep. This is also called a reduction reaction. We talk about these a lot in organic too. because it reduces the oxidation number of carbon, or the number of carbon-hydrogen bonds increases in a reduction reaction. You're reducing the number of CC, CO, or CF bonds, which is shown right here on this slide. So therefore, that happens when you're increasing the number of CH bonds. It's a hydrogenation reaction. If you're a visual learner, this is what that would look like. Palladium on carbon catalyst down here. The alkene kind of sits down on top of that surface. We add 2 new hydrogens down here. It's a radical reaction, okay, so you don't have to worry about knowing the mechanism for this one yet. But the key takeaway is, depending on the alkene that went into this reaction, we get different enthalpy values. Notice that in red here in this first column. These are all hydrogenation reactions, and more importantly, they all formed the same product. If we had different reactants and different products, of course we would have different enthalpy values. But here I have the same product, different reactants. Okay? So that tells me the reactant is important because I have these different enthalpy values. And I typically report these things as something known as heat of hydrogenation. All the heat of hydrogenation value is the enthalpy change for the reaction. We just report it as a positive number because these heats of hydrogenation, these enthalpy changes are typically negative. You just drop the negative and call it a heat of hydrogenation. It's just equal to enthalpy without the negative sign. In different values of heat of hydrogenation, even though we're forming the same molecule here, means that these alkenes had different stabilities. Let's look at why that is. Okay. Going to the same final product, the greater the enthalpy change here, between the starting and the initial, means that that must have been at the highest potential energy to begin with. Because the products have the same energy, we can correspond the change to the initial state. So the alkene that released the most heat must have had the highest potential energy to start, meaning it was the least stable. Conversely, the most stable alkene has the smallest heat of hydrogenation. And so jumping back a slide here, smallest heat of hydrogenation, 26.9, is the most stable. Highest, 30.3, is the least stable alkene. So if you repeat these experiments, what you see time and again is that the more alkyl groups bonded to the vinylic carbons, those sp2 carbons that are involved in the pi bond, the more stable the alkene. The more alkyl groups, the more stable it is. Or, if you want to think about it a different way, the more hydrogens that are bonded to those carbons, the less stable it is. Okay, so more alkyl groups is more stable. 4, more than 3, more than 2, more than 1. The only other thing to look out for, what if there's the same number of alkyl groups? Okay, in this case, 2 alkyl groups, 2 alkyl groups. Well, what do we see here? Different values of heat of hydrogenation. Cis has the larger heat of hydrogenation, meaning it's the less stable. So why the difference? Why is this one less stable? Well, these groups are just a little bit closer together, meaning there's more steric strain due to that electron cloud overlap. Similar argument to why we saw the equatorial position in cyclohexane was more stable, just because these groups have more space. So if you have 2 alkyl groups, trans is more stable than cis. So we can put that here, trans, more stable than cis, which is about the same as if the 2 are on the exact same side due to sterics in this case. But any of those would still be stable, more stable than something with just 1 alkyl group, for example. So that's really the biggest takeaway from this second video, or this third video, excuse me, from chapter 5. Know all the thermodynamic principles from the beginning of the video, which are largely review. Okay? And now know the difference in stability of alkenes. The more alkyl groups, the more stable something is, and it has a lower heat of hydrogenation.